Okay, here we are, lesson 1.2, the language of sets. You may be familiar with some of this material, but some of it will probably be new as well. A set can be thought of intuitively as a collection of elements. Could be cars in the parking lot, it could be numbers on a number line. Set roster notation specifies the elements of a set by writing them all out between curly brackets. So for example, curly bracket 1, 2, 3, curly bracket denotes the set whose elements are 1, 2, and 3. So this is the notation for a set that contains the numbers 1, 2, and 3. We often use ellipses when we're using roster notation if our list is really long or if our list is infinite. So for example, if I wanted to write out all the integers from 1 to 100, instead of writing them all down between curly brackets, I would do 1, 2, 3, ... to 100. Or if I just wanted to write all the positive integers, I would write curly bracket 1, 2, 3, ... Close the curly bracket. If S is a set, then the notation X, this means is an element of, and it kind of looks like an E for element. So X is an element of S. And then if you put a line through that little E, it means it's not an element of S. So X is an element of the set S, or X is not an element of the set S. Then we have this thing called the axiom of extension. It says that a set is completely determined by what its elements are, not the order in which they may be listed, or the fact that some elements might be listed more than once. So you can have two sets that look kind of different because things are written in a different order or repeated, but all that matters is what is in the set. Okay, we have some special sets for mathematicians. We have the set of all real numbers, which we denote with a capital bold R. We have the set of all integers, which we denote with a capital bold Z. That's positive and negative whole numbers and 0. And then we have the set of all rational numbers, or ratios of integers, and we denote that with a capital bold Q. Adding a superscript of a plus or a minus, or the letters non-neg, indicates that only the positive or negative or non-negative elements of the set, respectively, are to be included. So for example, the capital R with a little plus superscript, that means the set of positive real numbers. So instead of all reals, it just means the positive ones. Now, we have another way of writing down what elements live in a set instead of just listing them all in the roster notation. It's called set builder notation. And it looks like this, right? And you would translate this to words as the set. So the curly bracket is telling us that this is a set. So this is the set of all x's in S, the set of all x's in the set S, such that, that vertical line means such that, P of x is true. Okay, so we would say the set of all x's that are in S, that are in the set S, such that P of x is true. So P of x is just some property, P of x. Okay. So for example, we're going to describe this set in words and on a number line. So the set of all x's in the reals, the set of all x's in R, such that x is sandwiched between -2 and 5. Doesn't include the -2, doesn't include the 5. So I'm just going to label my number line here. We've got 0, 1, 2, 3, 4, 5, 6, -1, -2, -3, -4. It's good enough. Okay, so we're going from -2 to 5, all the numbers sandwiched between, not including the end points. So I'm going to put open circles at -2 and at 5, and shade it, the whole thing in between. So this would be all real numbers between -2 and 5. And then I should be careful to say not including -2 or 5. Okay, my next example, I'm looking at the set of all x's in Z. So I'm looking at elements of the integers, set of all x's in the integers, such that x is sandwiched between -2 and 5. So only integers this time. So let me just quick label this. Okay, so I can only do integers, so it's only at the tick marks, and I can't include -2 or 5. So I'm looking for integers between -2 and 5, not -2 and not 5. So like -1, that's in the set because it's an integer and it's between -2 and 5. Zeros in there, 1, 2, 3, and 4, but not 5 because I don't include the endpoints. So I could describe this just using roster method by saying -1, 0, 1, 2, 3, and 4. All right, and then for C, this one's just a little bit different. The set of all x's in the positive integers, where x is between -2 and 5. Okay, so I can only choose x's from the positive integers, so that means nothing negative is going to be included. So I have to choose positive integers between -2 and 5, not including either endpoint. So the first positive integer between -2 and 5 is 1. And then I've got 2, 3, and 4. Those are the positive integers and before you hit 5. So if I use the roster method, I would have 1, 2, 3, and 4. Okay, moving on to subsets. If A and B are both sets, A is called a subset of B, which we would write A is a subset of B. If and only if every element of A is also an element of B. So that is A is a subset of B, means that for every element X, if X is in A, then X is in B. Sometimes we use a Venn diagram to describe this. So here's B, and then A would be inside of it. So every element in A also lives in B. Sometimes we read A is a subset of B. Sometimes we read that as A is contained in B, as an alternate to A is a subset of B. I like that one personally because this looks like a C, so I would read A is contained in B. And that little line underneath means or equal to, right? So A is contained in or equal to B. So an alternative Venn diagram for A is contained in B could be B is the bigger one, right? But then A could be the entire thing. So if they could also be equal. Every X in A is also in B. If you put a line through that little C, we say A is not contained in B, or A is not a subset of B. That is, there would be at least one element of X that is in A and not in B. And then the next term is proper subset. A is a proper subset of B in this case. This is a picture of a proper subset where A is fully contained within B, but it's not all of B. Okay, so A is contained in B, but A does not equal B. And the notation for that is often denoted with the C without the line under it. A is strictly contained in B, or is a proper subset of B. Okay, so here we're given three sets. A is the positive integers. B is the set of all n's in Z, so the set of all n's in the integers such that n is between 0 and 100. And C is the set 100, 200, 300, 400, 500. And we want to determine which statement below is true, whether each statement below is true or false. Okay, is B contained in A? So B is 0, all the integers from 0 to 100, including 0 and 100. Do all of those numbers live in the positive integers? Almost all of them do. The only problem is 0. 0 is in the set B, but it's not in the positive integers because 0 is not positive. So this one is false because 0 is an element of B, but 0 is not an element of A. Okay, so for B to be contained in A, every element in B would have to also be in A. Okay, B, C is a proper subset of A. So C is 100, 200, 300, 400, 500. Do all of those numbers live inside the positive integers? Yes. Each of these numbers are positive integers, so this lives within the positive integers. It is a proper subset. I'll write true. Okay, part C. C and B have at least one element in common. So C and B. Okay, so B is all the numbers from 0 to 100. 0, 1, 2, 3, 4, blah, 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 up to 100, including the 100 because of this or equal to. C has a 100 in it as well. So B and C both have the number 100 in the set, so they do have that in common. They share 100. Okay, C is contained in B. Is C contained in B? So 100, 200, 300, 400, and 500. Do each of these numbers exist inside of this set? No, only one of them does, not all of them. So C is not completely contained in B. And then is C contained in C? That is true. Any set is always a subset of itself. As long as we're not talking proper subset, and we have this little line under here, then yes, every element of C is also an element of C. That's the definition of subset. Okay, here we have some tricky statements that we want to determine if they're true or false, and this is just a little practice with notation. So for part A, 2 is an element of the set 1, 2, 3. That's what this says. 2 is an element of the set 1, 2, and 3. Yes, this is true. This is the set that has elements 1, 2, and 3. So 2 is an element of. Now, a little bit trickier, the set that contains the number 2 is not an element of the set that contains the numbers 1, 2, and 3. Okay, so this is a set. It is a subset, but it is not an element. Okay, so this one is false. To make it true, we would have to look at part C here. Part D is how we would make it true. So the set that contains the number 2, that is a subset, is contained in the set 1, 2, 3. So this one is true. And then for C, 2 is, this says 2 is a subset of 1, 2, 3, is the set 1, 2, 3. This is not true because 2 is a number, not a set. Okay, for this to be a set, we would need curly brackets around it to make that look like the set 2 that contains the number 2. So this one is false. Okay, a Cartesian product. This is a special kind of set where the elements are ordered n-tuples. You probably have heard the word ordered pair, when that's like a 2-tuple, right? So, or a couple ordered pair. So if you're given sets A1, A2 to AN, the Cartesian product of them is denoted with this like multiplication symbol, the cross. A1 cross A2 cross da 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 cross AN. That's the set of all ordered n tuples, where you would take elements from each of the sets and they make elements of the ordered n tuple. So this looks a little crazy, but let's just jump down to our example. Okay, R cross R. So the reals cross the reals. So that's like, instead of calling these sets A1, A2, AN, right? We're going to talk about an actual set, the reals. Okay, so we're going to do the reals cross the reals, also known as R2. If you've taken another advanced math class, you may have seen it like that. That's just the two-dimensional Cartesian plane that we are very familiar with, right? Each element of R cross R is an ordered pair, instead of using n tuple, I'm using the word pair. I guess you could call it a two tuple, but it's an ordered pair, x comma y, such that x comes from the first set, the reals, and y comes from the second set, the reals. So it's just the coordinate plane, also known as the Cartesian plane. So there's a picture, I've plotted a few points in here. Okay, so here's an example where I have just a couple of small sets. A is the set XY, B is the set 1, 2, 3, C is the set AB. All right, I want to find A cross B. So it's a set of all ordered pairs where the first element lives in A and the second element lives in B. So A cross B, it's a set, and the elements of the set are ordered pairs. First element has to come from A, so I could start with an X, and then the second element comes from B, so I could do 1. And I want to list all possible pairs like this, so I could have X1, X2, X3. All right, so that's all the ways I can pair X, the first element of A, with every element of B. And then I'm going to move on and look at the second element of A, which is Y, and I want to pair that with every element of B. So A cross B is a set of ordered pairs, and every element of A gets paired with every element of B. Okay, in the same way, we'll do B cross A. Okay, so I want to list all the ways I can pair elements of B with elements of A. So the first element of B is a 1, and I could pair that with the X or the Y from A. And then my second element of B is a 2. It can get paired with X, or it can get paired with Y. And then my third element of B is 3, and it can get paired with X from A, or it can get paired with Y from A. Okay, A cross A. So I find it helpful to write A is XY and A is XY. I just like to see those two things in front of me. So A cross A, I'm going to pair an element from A with each element from A. So XX or XY. And then the second element from A is Y, and it can be paired with an X or a Y. And how many elements are in each of those sets? A cross B had 6 elements, B cross A had 6 elements, and A cross A had 4 elements. Okay, I think I took this one off, so we'll skip that. Okay, an important object with relation to a set is called a string. This is important in math and in computer science. Given a finite set A, a string of length n over A is an ordered n tuple of elements of A written without parentheses or commas. The elements of A are called the characters of the string. All right, so we're going to let A be the set that contains elements 0 and 1, very common in computer science. And a string over this particular set, zeros and ones, is called a bit string. So I want to list all the strings of length 3 over A that have at least 2 characters that are the same. So I have to decide which character I need to, that I'm going to have repeat, that I'm going to have at least 2 of. So I'm going to start with the 0. So if I want 2 zeros, at least 2 zeros, I could have 0, 0, 1, 0, 1, 0, or 1, 0, 0. That's exactly 2. I could also have 3 zeros. I could have 0, 0, 0. So all of those have at least 2 zeros. And there's no other string I could create. There's no other order I can write them in that would give me at least 2 zeros. Now I have to write all the strings that have at least 2 ones. So I could start with the 2 ones. I could have a 1, and a 0. And then I could move the 0 to the middle. I could have 1, 0, 1. And I could move the 0 to the front, and I would have 0, 1, 1. And that's all the ways I can have exactly 2 ones, but then I could also have 3 ones. And all of those have at least 3 ones. So those are all the strings of length 3 over A, the set 0, 1, with at least 2 characters that are the same. Okay, so the null string over A is defined to be the string with no characters. So like you don't write anything down, it's called the null string. It's often denoted lambda, and we say it has length 0. So these guys all have length 3 because there are 3 elements in the string. If you don't write a string down, it has length 0 because there are no elements in it. Now, in computer programming, it's important to distinguish among different kinds of data structures and to respect the notations that are used for them. Similarly, in mathematics, it's important to distinguish among, say, the set of elements ABC, the ordered thruple ABC, and the string ABC, and so forth. These are all significantly different objects.